Hello, good to have you back with us for the second topic of MOOCOR. In the previous topic, we introduced the concept of feasible region and extreme points. In this topic, we will be talking more about extreme points and feasible region, plus we are going to introduce the graphical solution to LPs in 2-dimension, of course, that we can plot that. And then we would delve into a standard form of LP. We will introduce the standard form and we will introduce new variables and new concepts which are important in operations research. These variables that are called slack variables or surplus variables will be introduced shortly in this topic. By the end of this topic, our goal is to learn more about extreme points, about the feasible region, introduce the graphical solution and the concepts of finding an optimal solution and the approach to do that graphically, and the role of slack or surplus variables in the solution. Let's first look to see what we did last time. We are going to take a minute or two and go over some of the important things that we talked about last time. This time we are going to introduce new concepts. But before I get into these new concepts for you, I would like to go back to what we had done before and add a little bit more clarity to some of the cases that might arise when we deal with the feasible region. Last time we looked at some constraints which were in the form of less than or equal or greater than or equal some numbers. This time we would like to also consider the case that there may be a constraint which is in the form of an equation. What happens if we have an equation? Here is an example. Let's take a look at this example and see how we are approaching it. In here we have an equation. The rest of the feasible region is easy to construct. So let's construct the first 3 constraints. We are constructing line 1, line 2, and line 3. Now, the 4th line is in the form of an equation. We will plot the line the same way that we have been plotting the other ones. Now this line passes through the feasible region, so you can see that the only acceptable solutions are the piece of the line which is inside the feasible region. So when you are introducing an equation, for example, into a set of constraints, then that equation really takes over. And if that line or that equation passes through the feasible region, then you would have a feasible region, which is basically the piece of the line inside the feasible region made by the other lines. If we have 2 equations, then the answer is at where they are intersecting. Now this is an important consideration because it, as I mentioned, it forces us to just be restricted to the piece of the line which is actually inside the feasible region made by the other constraints. Now let's concentrate on the material that we are going to be covering in Topic 2. In Topic 2, we are going to start with finding an optimal solution, the best solution based on the objective function that we are given. And because we are still concentrating on 2 dimensions, we will be able to plot the objective function line as well. There are 3 steps that we have to go through. First, construct a feasible region from the given constraint set. Second, plot the objective function. The point in here is the objective function is not in the form of equation or an inequality. Objective function is just a function given based on x1 and x2. So how do we plot that? In this case, we are going to plot the objective function based on an arbitrary value that we will assign to that. So we will plot the objective function assuming that this value of objective function is equal to some number. In Topic 1, we talked about the lines which are parallel to each other, and the only values that need to be changed is the right-hand side of the equation. So we need to find, if we move this line parallel to itself in one direction or the opposite direction, would the value of objective function increase or decrease? In the third step, we will slide this objective function line parallel to itself toward the direction that objective function is asking us. If objective function is a maximization problem, we will slide the line toward the direction of increase. If it is minimization line, we would slide it toward the direction of decrease. In both cases, our goal is to find feasible solutions. So this line has to first intersect with the feasible region and then move toward one of the extreme points. As we are moving the objective function line, we will have our optimal solution, and this optimal solution will happen to be at one of the extreme points, and that's where the importance of those extreme points are very clear, that the optimal solution is at an extreme point. Whether it's maximization or minimization, it will be at an extreme point. So let's take a look at one example, and for this example I have selected the problem that we had as a test question for Topic 1. So let's look at this. This problem is given as a maximization of 5x1 plus x2 subject to a set of constraints. This is the solution to that test problem. This is the feasible region of this set of constraints. Now we are going to pick up an arbitrary value for the objective function, 5x1 plus x2, and I'm going to assign this to be minus 5. I'm going to plot 5x1 plus x2 equals minus 5. I have plotted the line, which is shown in here with the color red. Now I need to find out what happens when I slide this line parallel to itself. In this case, toward the feasible region. This is below the feasible region. If I'm sliding it towards the feasible region, would these z values be increased or decreased? To find that out, I'm going to plot one of those lines, and that line is the simplest one and the easiest one, the line that passes through the origin, which both x1 and x2 are 0. Therefore, the objective function value is 0. So the objective function line of the value 0 is the one parallel that passes through the origin. Now, from -5 for the first line that I drew to 0, apparently I am moving in the increased direction. So I'll put a little sign in here to identify that this is the direction of the increase. So I'm going to slide it towards the feasible region because it's keep getting increased, and that's what I'm trying to find. I'm trying to find the maximum of this function. So I'm going to slide it until this objective line hits the feasible region, and as I slide it further and further, it keeps increasing. The function value, the objective function value keeps increasing until I get to this specific extreme point. As soon as I slide it any further, then all the solutions are going to be infeasible. All the solutions on that line, on that z line, are going to be infeasible. So that extreme point is the last feasible point that I can have for this problem. And that is the maximum that I can achieve using this feasible region. And that is the optimal solution of the problem for me. Now, if this problem was minimization, let's start from the first line that we drew. We drew the line of z equal -5, or the objective function value equal -5. And I'm trying to minimize the objective function. Well, because the direction of increase is towards the feasible region, then that is probably not where I want to go. However, there is no feasible solution where the z line is right now. So I will move the line, I will slide it parallel to itself, and the moment that it hits the feasible region, the first extreme point that it comes in contact with, that will be my optimal solution for the minimization problem. Now let's look at both maximization and minimization on the same graph. You notice that they are parallel to each other for the same objective function, and they are on two opposite ends of the feasible region. In this case, we saw how the solution was achieved. Is there any difference with different type of graphical solution? Really not. There may be a couple of things here or there, but that's essentially how it is handled. What happens after you find the optimal solution? Then you will be reporting the value of the objective function at that point, and x1 and x2 values that will achieve that objective function value. So this is a very simple process. It's not a complicated process at all. Now we want to look at a couple of cases that might arise. One, what if one of the constraints is in the form of equation? Well, it goes back to what I discussed at the start of this topic. If one of the constraints is in the form of equation, then the solution is only on that line, the piece of the line which is enclosed by the feasible region of the other constraints. Process is still the same. We will still plot the objective function line. We will slide it toward the direction of increase or decrease depending on whether the problem is maximization or minimization. And then as soon as we hit the line, it's either the lower end of the line or the upper end of the line. one of the two ends of the line in the feasible region. That end of the line could be at a corner point of the feasible region of the others, or it could be on the line from one of the constraints. Okay, I believe that's enough for graphical solution. It's a very simple concept and it follows our discussions that we had before. Now let's look at a more important concept, and that's the concept of slack or surplus variables. Remember, having a feasible region means that you have infinite number of solutions. Anything inside the feasible region or on the boundary of the feasible region is a solution to the set of constraints that you have. To solve this mathematically, we need to convert these inequalities into equations. Again, with the two variables, it is easy to do it graphically. But we are doing the two variables to talk about the concepts, such that when we talk about more variables, then since we cannot plot them, we will have an idea that we can look back at the two variable and say, oh, that's how it was, or that's how it is, and make it something that we are comfortable discussing. So again, in this case, we are still in the two-dimension environment, but what we are talking about is the same as if we had 5, 10, or 20, or 10,000 variables. The main concept in here is to introduce a new variable into an inequality to convert that into an equation. An inequality which one side of it is larger than the other side or smaller than the other side can be converted into an equality. You can balance it out if you add a variable which is equivalent to the difference between the two sides. In this case, we have x1 plus x2 less than or equal 10. If I introduce a new variable that is equal to the difference between the two, the difference between 10 and whatever x1 plus x2 is, then I would have balanced them out. Because x1 and x2 will change, this variable also will change. I will keep it as a variable, and I will use the notations of s for this variable, and for constraint 1 I will call it s1, for constraint 2 I will call it s2, and for constraint 3 and so on. Now, if it is less than or equal, I have to add something to the left-hand side, like in this case. So it would be plus s1. However, if it is greater than or equal, like this second constraint, in this case I have to subtract. So in this case I will have minus s2. Remember, s1, s2, and all these variables that we are adding as a slack variable or surplus variables, they have to be greater than or equal to 0. Otherwise, you cannot make your cases. When we are adding a variable, we will call that slack variable. When we are subtracting, we will call that surplus variable. I'm usually referring to all of them as a slack, but the correct terminologies are those. And this is an example. Look at that, and in this case I have 4 constraints. 2 of them were less than or equal, and 2 of them were greater than or equal type constraints. So I have added two slack variables and subtracted two surplus variables. I should not forget to add that condition for them to be greater than or equal to. Two important observations. One, if there is an equation in the constraint set, because it is already an equality, you are not going to add any slack or surplus variable to it. The second thing is that we will separate the main constraints from the special constraints, which usually represents the non-negativity conditions. We are not going to add slack or surplus variables to any of those variables, and these are the variables such as x1 greater than or equal 0 or x2 greater than or equal to 0. To these we are not going to add any slack or surplus variables. When we convert the problem into this format, we have the standard form of the LP. This is for the constraint set. There's also a standard form for the objective function. For the objective function, this is what we do. We are going to call this function z and then move everything to the left-hand side. So z will be like a new variable for us. So it will be now, so it will now be in this format that you see equals to 0. This form of presentation is called the standard form of the LP. Standard form of the LP is important, and that is where we usually start solving the problems through the algorithms that we will introduce later. Now let's look at an example problem, and in this case I did not even restrict myself to two variables. I used more variables, as you see, but essentially the process is the same. Okay, now we have introduced the standard form of the LP, slack variables and surplus variables. Now what? How would they come into play in the solution procedure? Because we just looked at the graphical solution. I didn't need a standard form for graphical solution. The argument had nothing to do with the slack or surplus variables. So why are they important? Why should we do that? Again, it goes back to what we will be discussing for regular problems. There's no way for you to visualize them. But if you understand the concept of a slack variable, then you will understand what is going on as you progress towards the solution of an LP. So in this graphical format that I have, how can I see the values of the slack variable? Because in here I only can see x1 and x2. Let's go back to the same problem that we just discussed. As you notice, there is no s1, s2, or s3 anything in this problem. The only values that I have are x1 and x2. So where is s1, s2, and s3? Let's consider one of them. Let's consider that first line. That line representation is this line in the graph. Now the line itself represents the equation. That's how we plotted the line. We set it equal and we plotted the line. So the line itself represents the equation. And if left-hand side and right-hand side are equal, then what about the value of a slack? Then the value of a slack is 0 when you are on the line. So if you pick a point on that line, the value of a slack for that line is going to be 0. What if you move away from that line? In this case, if you move away from this line towards the infeasible region, how would you know that you are at an infeasible solution? Well, x1 and x2 will give you just values. In this case, x1 and x2 has to be greater than or equal to 0, and it is. So what is that is going to show you that you are at a infeasible point? It's that a slack variable. What does that point represent? It represents the areas that this constraint is infeasible. This line, remember, the solution of this line is toward this way, and that is the infeasible solution of the line. Well, mathematically, what is going to let you know is the value of the slack, and it would represent it with a negative number, thus violating this important set of conditions that slack variables have to be greater than or equal to 0. Let's plug in 1 point in there. You see, to balance this out, slack has to become negative, and that is the sign of infeasibility that we will have in here. What if I move towards the feasible region? Well, and as I'm moving towards the feasible region, slack becomes positive. So for any point to be feasible, it means that the slack variables for all constraints have to be greater than or equal 0. So if I pick, for example, that point inside the feasible region, you will notice that all calculations show that the solution is feasible, but all slack variables to be, slack and surplus variables to be greater than or equal to 0. Now this is a system. You cannot make the decision just based on one of the slacks. It has to be on all of them. For example, if you keep moving down, and I've already left the feasible region, that slack is still positive. So there is another slack that is going to be violated. What if, and this is important, what if I'm at an extreme point? That extreme point, for example. Well, this extreme point in this case is the intersection of two lines. Well, this point, this extreme point, is on both lines. What does that mean? It means the slack variable for both lines is 0. That is an important indication that you are on an extreme point. Again, it doesn't tell you whether you are on a feasible extreme point or an infeasible extreme point. It will tell you that you are on an extreme point. To know whether you are feasible or not, you have to look at the rest of the constraints. You have to make sure that all these special constraints, all of them, are satisfied. So let's look at what we discussed in here. We will use slack variables or surplus variables for converting the problem into equations. If there is a constraint which is in the form of equation, we are not going to change that. We are not going to add any slack or surplus to that. We will not add slack or surplus to the special set of constraints, which are usually the non-negativity constraints. We will convert the objective function also into a standard form. When we convert the problem into a standard form, we will drop the word max, we will drop the word subject to, and we will consider the problem just like a set of equations. This standard form is the basis of solution approaches that we have. But understanding what is slack variable and their role in the solution process is very important. Thank you for watching.